So hello everyone, this is lecture 15 for the mathematical physics in which we were studying the matrices, and in the last lecture we were discussing about the inverse of a matrix. So we see that here is the formula for inverse, that is 1 upon determinant A. Cofactor matrix ka transpose. Okay, this was the formula. So let's see some examples. If here is this matrix A equal to 3 2 1 4, then determinant will be this. And you know how to find the cofactors, that is for 3 it will be 4, and sign will be according to this 1 plus 1 2, that will be plus, and for 2 here it is second row first column, so it will be minus, so minus 1 c2 1 1, and for it will be minus 2, and for 4 it is 3. So you can find the cofactor matrix. Then taking the transpose you can find this is also called the adjoint of a matrix. Okay, so just find this determinant you have. Now you can find the inverse, that will be 1 upon determinant A, then this. So this will be inverse of A. Same you can apply it for the 3 into 3 matrix, that is this. Okay, try to solve that. Let's move on to the forward topic. So if there is this matrix, that diagonal matrix, how to find the inverse of a diagonal matrix? So what is a diagonal matrix is that all the elements of a matrix other than the diagonal elements will be 0, and all the diagonal elements will be non-zero. Okay, so here is this aij n into n. Aij will be 0 if I is not equal to j, that means non-diagonal elements, and aii is not equal to 0 means the diagonal elements. So you can find the inverse directly. Okay, just remember this. If it is a diagonal matrix, then just inverse will be, the inverse elements will be 1 upon a11, 1 upon a22, and 1 upon ann. For example, you have this matrix, the diagonal matrix. So if you want to find the inverse, then just reciprocal of these term elements, that is 1 upon 0.5 will give you minus 2, 1 upon 4 and 1. So this will be A inverse. Now we have some properties of inverse that you can apply if there are multiple matrices. So if there are product of two matrices AB, the inverse will be B inverse A inverse. And if there are n matrix A, B, C, D, E, F, G, H, then just take it in the reverse order, and it will be Q inverse, P inverse, and up to C inverse, A inverse. Okay. Now, if A to the power n, this is also a functional matrix. We will study about it later. But we can use the property here, that is the inverse of A to the power n will be the nth of A inverse. Okay, this will also a functional matrix again. So just remember this property. And also A inverse, the transpose of A inverse will be equal to the inverse of A transpose, and the inverse of A equal to A. Okay, now if a matrix is symmetric, then its inverse is also symmetric. Okay, just remember this. These properties can be useful in the exam for solving question directly. Now we have an example where how we can use these properties, so you can get an idea. So they consider there are two matrices n into n, order A and B, such that A plus B is invertible. What does that mean? If it is said that it is invertible, means the inverse of this matrix will exist. The inverse of A plus B matrix will exist. Okay, so we have the given in the question is C equal to this, D equal to this. It is A plus B inverse B, and D is B, A plus B inverse A. So which one is true? There were four options. Okay, and one of the options was this, C equal to D. So how we get this? So let's solve them from the given information and take the inverse of C. C inverse will be, we know that for the inverse property use this, just AB inverse will be B inverse A inverse, means in the reverse order. So if we take the inverse of C, then it will be B inverse, inverse of this, inverse of this, inverse of this. So B inverse A plus B inverse, inverse will give you A plus B, and it is A inverse. Same apply for the D. D inverse will be A inverse, A plus B inverse, inverse will give you A plus B and B inverse. Okay, so here you can just distribute them inside, and you will get B inverse A inverse plus B inverse B A inverse. This will give you identity matrix A inverse, and here B inverse B will give you identity matrix. So after solving this, you will get B inverse plus A inverse. So C inverse will be equal to this, and Similarly, solving for this, you will get A inverse A B inverse plus A inverse B B inverse. This will be identity matrix, this will be identity matrix. You will again get B inverse plus A inverse. And we know that A plus B and B plus A are both commutative and they are equal. So we can say this equal to this and C inverse equal to D inverse. Taking the inverse both sides, we'll get the C equal to D. So this type of question will be seen in the exam, and you can solve them like this. Okay, there are some tricks you can apply and all you will use these properties there. Okay, so just take them lightly. Now we have a new concept here, that is matrix eigenvalue problem. Now you have heard about it often in the quantum mechanics, in the classical mechanics, and many of the other things, other subjects. That is eigenvalue. So all comes from this mathematical subject. Okay, so what is the meaning of this eigenvalue for a matrix? As you have seen in the quantum mechanics, we have matrix all around. For all the operators we have matrix, and we find the eigenvalue. So here is the base. What is this eigenvalue? So let's see. Let A equal to Aij n into n. Okay, this is matrix. Then consider an equation Ax equal to lambda x, where x is an unknown vector, and A is a matrix, which for which we have to find the eigenvalue, and lambda is unknown scalar, and we want to determine both. Means x is a unknown vector and lambda is a known scalar value, and we need to find both of them. Okay, so first let's see this equation, what this denotes. Means x is a vector, that is a column vector, A is a matrix. When you multiply this, then you will get a column vector, and that column vector will be again parallel to this x vector, because we have it is given that this will be equal to lambda x, and lambda is scalar. Means whatever we get from this will be parallel to lambda x. Okay, so that vector we get, which is parallel to lambda x, we call that vector as eigenvector. Okay, and the value which is multiplied, means that vector we get, that value is called the eigenvalue lambda here. Okay, so let's see it again. If r equal to ax equal to lambda x, okay, then r is that vector we get, column vector, and that will be parallel to x. Means the component of A that will be parallel to x, we call that eigenvector. Hope you get the idea what I am trying to convey here. Now a value of lambda for which equation has solution. Now value of lambda for which equation 1, that is this, has solution, means x should not be equal to 0, other solutions, is called eigenvalue of the matrix A. Okay, the corresponding solution x is not equal to 0 is called the eigenvector of A, corresponding to eigenvalue lambda. Means for each eigenvector we have each the discrete eigenvalues. In matrix notation, equation 1 can be written as, means this equation can be written in the matrix notation as this. Means you can see that take it at the left hand side, and here it will be 0, and if you take the x common, then you need to minus lambda from A, and lambda is a scalar and it is a matrix, so you will multiply with identity matrix here, lambda I, so you will get A minus lambda I x. Okay, because you can only minus a matrix from a matrix, that's why we multiply the identity matrix, because ix will give you x again, so you will get this equation again. Okay, so you get this equation. Now this A minus lambda I and x, this equation is a linear system of homogeneous equations. You know what is this linear system, I already told you in the previous lectures. Means where you have nothing in the means it's like ax plus bx plus cy equal to 0, this type of equations, these are called the homogeneous equations, linear equations. Now for them, if this term is non-zero, then this must be 0, and 0 will be a trivial solution, then we will get the trivial solution. Means if this A minus lambda is non-zero, then we will get the trivial solution, and we don't need trivial solution. What we need is non-trivial solutions, and for that this must be equal to 0, A minus lambda I. So that's how we will go forward. Means this should be equal to 0, and then we will solve for it. For non-trivial solutions, A minus lambda I should be equal to 0. Now we have these. So if there is any matrix A of nth order, then you will get this type of matrix after solving this. A11 minus lambda means all these are diagonal elements will be subtracted, means lambda will be subtracted from them, and you will get when this determinant, you solve this determinant, then you will get a quadratic, not just a quadratic, you will get a polynomial of powers of lambda, and that equation is called the characteristic equations. Means when you just solve this, if it is 2 order, means 2 into 2, then you will get a lambda square in the equation. When it is 3 into 3, you will get a lambda cube. For 4, you will get lambda 4. So that is a polynomial you will get, and that equation is called the characteristic equation, and this determinant is called characteristic determinant. The equation is called the characteristic equation of the matrix A, polynomial of nth degree in lambda. Okay, so the power of lambda will be equal to the order of the matrix. Hope you get the idea. Now how to find the eigenvalue and the eigenvector? Let's see. First calculate the eigenvalues, then corresponding eigenvectors. So after solving this characteristic determinant, you will get the values of lambda, that will be called the eigenvalues. First solve the eigenvalues, okay, then we need to find the eigenvectors corresponding to those eigenvalues. If we get all the eigenvalues different, means no two eigenvalues are same, then they will call the non-degenerate eigenvalues. For these we will get a distinct eigenvectors, discrete eigenvectors for all of them, and all are linearly independent. All eigenvectors we will get will be linearly independent. Now if we get the repeated eigenvalues after solving this, means two eigenvalues are same, then we will call them degenerate eigenvalues. Repeated eigenvalues are called degenerate eigenvalues. For these there are different eigenvectors, means for the same two eigenvalues we will get different eigenvectors. Okay, they may or may not be linearly independent, and those eigenvectors may or may not be linearly independent. Okay, so just remember these lines, and we also get some equations like the sum of all the eigenvalues will be always equal to trace of A. Okay, what is the trace? Trace is the sum of all the diagonal elements, so that will be equal to sum of eigenvalues. And if you find the product of eigenvalues, that will be equal to the determinant of that matrix. Just remember these are very helpful equations. Now if they are linearly independent, then they will follow the orthonormality condition. That is, you know what is inner product, that is we have two eigenvectors, these are column vectors. You can't directly multiply them because both are 1 into 3 order. So first we need to transpose this first one. So if you transpose this, then it will be 1 into 3 and 3 into 1, you will get the product. So any two eigenvectors will be orthogonal. And what does that mean? That mean values will be given by this Kronecker delta. If I equal to j, then we will get 1 of this value, and if I is not equal to j, then that will be 0. Okay, how it is 0? Because both are linearly independent, so their product will be 0, and if both are same vector, then we will get 1. Okay, just remember this. So we need to define some more terms, that is length or norm of x. X is eigenvector. So what is the length or norm of this vector? That is under root of the inner product of that vector. Okay, so how you find the inner product? Just transpose of this, x transpose x, and the under root, you will get the length. This is for the real vectors. If you will get the complex vector in the equation, then how you will solve? So first take the transpose of this. Okay, these are two vectors and these are complex. Then you need to you have to take the conjugate transpose of the first one, then multiply with the second one, and you will get the length. How? Just take the under root, means orthogonality will be like this, and for the length or norm, you will go like this. And when you try to normalize the vector, okay, in the quantum mechanics or anywhere, so you need to put the value of this norm or length equal to 1. Okay, when you put it 1, then you can normalize the eigenvector. So we'll see in the next lecture how to normalize and how to use these equation and how to find eigenvalues. Means we will take the examples exactly. Okay, So we'll see this example in the next. Okay, thank you. Bye bye everyone.